Hello, my name is Howard Snap. I'm a local biology teacher at Firestone High School, and today I'm going to be teaching you about the ideal gas law. Now, as you know, gas is all around us. It's very tiny particles rapidly mashing together, and it moves at an alarmingly fast rate, filling up our entire atmosphere. Now, you've already learned about the combined gas law. The combined gas law is a very useful equation that allows a scientist to discover the temperature, volume, or pressure of any enclosed gas. Now, this is a great equation, but there's only one problem, and that is that it assumes the amount of gas is constant. Now, here's where there might be just a little bit of confusion. See, the combined gas law equation gives the volume of gas, not the actual amount. So the difference is, if you remember, gas is just a bunch of tiny zooming particles, and it can expand to fill any container, any volume, and that's a unique property of gas. But the amount of moles is not in the volume specifically. So here's an example. Say we have 10 moles of oxygen and we put it in an enclosed container. If we were to expand the container, the volume of gas would go up, the pressure would decrease, but there are still 10 moles in that container. See, the amount of moles and the volume aren't necessarily correlated. Alright, now back to the combined gas law. See, the only problem with the combined gas law is that it does not list the amount of any given gas. See, for that we use the Puvner equation, the ideal gas law, which is pressure times volume equals moles times R times temperature. There are some interesting symbols to note in this equation, and the first is N. See, N in this equation stands for moles of any substance, and it's kind of weird because you'd think that M would stand for moles, but that's actually not the case. That's because there are a lot of variables in the chemistry world that use M, and if we used M for moles, it would just get too complicated and cluttered up later down the line in chemistry. So the other interesting variable is R, and that stands for the ideal gas constant. R is 8.31 liters per kilopascal. So remember how that each mole of any gas at standard temperature and pressure is 22.4 liters? Well, standard temperature and pressure is 101.3 kilopascals and 273 degrees Kelvin. And if we want to get a value we can use for R, that is 8.31, we need to derive it using some dimensional analysis. First, we'll take 101.3 kilopascals and multiply it by 22.4 liters, and then we'll divide that number by 273 degrees Kelvin. So when we plug that all into our calculator, we get, surprise, 8.31 liters per kilopascal. Anyway, now that we have all our variables, we now have the complete ideal gas law, PV equals nRT, or Puvner. Sounds kinda like pervert, yeah. Now we're going to use our new rule to solve a problem. When the temperature of a rigid hollow sphere containing 685 liters of helium gas is held at 621 degrees Kelvin, the pressure of the gas is 1.89 times 10 to the third kilopascals. How many moles of helium does this sphere contain? Alright, that problem sounds kind of complicated, but it's really easy if we break it down. First, we're going to take our pressure, which is 1.89 times 10 to the third kilopascals, that's the P in our equation, and then we're going to multiply it times the volume, which is the V, and that is 685 liters, and then we're looking for moles, so we're going to skip over that part, and we're going to multiply times 8.31, which is our ideal gas constant, and then we're looking for a temperature, and it says our temperature is in 621 degrees Kelvin. Alright, so there are some important things to note also. Make sure that your volume is always in liters, otherwise our ideal gas constant, which was solved in liters, won't work. And also on the same note, make sure in temperature you're using Kelvin, because for the same reason our ideal gas constant will not work if your degrees or volume are in other measurements. Now that we have that all plugged in, it's pretty much just plug and chug from here on out. So we're going to divide one half of the equation by the other. And so n equals 1.89 times 10 to the third times 685 divided by 8.31 times 621. So plug that into your calculator and make sure to add parentheses or your whole thing will mess up. And we get 250. The answer to this problem is 250 moles of helium. Bam! And now in conclusion, here is a picture of Ronald Reagan and his buddies watching the season finale of Breaking Bad.